Okay, so today we're going to do system ID from a Bode plot, right? And, you know, we've already had an exam on Bode plots like this, right? Okay, where this is a low pass filter, right? We've done Bode plots for a high pass filter. All right. Now, we've also done where we have repeated real roots, where we've raised this. Okay. And we've raised that. All right. So, yeah, low pass. Passes low, right? High pass. Passes high. Now, we haven't really done this in a while, so you know, what is the Bode plot, right? Well, plot the magnitude of HS, right? And phase of HS with or against the log of the frequency or omega. All right. And then the magnitude is 20 log. Right. And yeah, we just substitute S equals J omega, which is the Fourier transform. All right. So it could have felt confusing where and yeah, I know I might not be known for reviewing, right? But the Laplace changed time into frequency with a real and an imaginary part. Okay. And we could have a pole, right? A zero. We could have poles. Poles on the imaginary axis are unstable. Poles with a real positive real component are unstable. stable things are over here, right? But so when we talked about Laplace, we were talking about the complex plane, right? And then we went right into Bode, which it's really just S equals J omega, right? And you get these kind of shapes, right? Now, you try to put the important things first in a course. So things like, you kind of have to understand convolution and time domain response and step response and impulse response. And then you go into the Laplace transform because we use that again and again and again, right? But we kind of jump into this frequency where S equals J omega, even though it's a Fourier thing, and even though the book, filters are in chapter 6, right? Because we're really using the Fourier transform, and if it, you can, right? You can just, I think that's a plus. No, it's got to be minus. And you can see that it's the same thing, except this is only on imaginary axis, and just think of them as sine waves, all right? But really, you don't have to go into a full-blown Fourier transform, teach you everything about it, when really it's just Laplace. In some cases, you can think of it as just a special case of Laplace, right? And so if I have omega naught S plus omega naught, and I plot the magnitude of that, well, there's a pole here. I'm kind of terrible at drawing this, but the transfer function plotted right at omega naught is going to look like this. It's just, it's circular and it goes to infinity as you approach omega naught, right? But we just calculate that's what the actual plot looks like, right, on the complex plane. But when we just sweep J omega, all right, from negative to positive, right, that's where we get this. I'm not gonna. Let me try to draw it a little better. Is that if over here in the complex plane, I have a pole that goes to infinity, right? And it comes like this. But on the complex plane, it does that kind of shape. I'm going to just let it go. All right. So the thing is Laplace has plus J omega, minus J omega, plus the real part, minus the real part. And the Fourier transform has minus frequency and plus frequency. Now, you might ask yourself, where does the J go? Well, we're just plotting, these are just sine waves with a certain frequency. We substituted J omega. So we just kind of pull it out and we just say, oh, and you get this kind of thing, this shape. All right. Because you have 20 log square root of omega naught squared, right? Because that's just the real part. There is no imaginary part. And then on the bottom, you get 20 log omega squared, because it's the magnitude is the imaginary part squared. You get rid of the J, right? Plus omega naught squared square root. Here's the frequency. And it doesn't say anything that it's got to be positive. Now, when you do the Bode plot and take log omega, you can't be at 0 anymore, right? And then so you get close to it, but you just can't be at 0, all right? Now, yeah, how would we calculate this, like if we were programming the Bode plot, right? Well, the magnitude would be of the numerator would be 20 log square root of omega naught squared, right? And then over here, well, you would have to substitute J omega. So you have J omega squared plus 2, oh, there's an S there, 2 omega naught J omega plus omega naught squared. Now, this, right, turns into minus omega squared plus omega naught squared, right? I'm going to square that. This becomes 2 zeta omega naught omega squared square root 20 log. And yeah, you would just substitute in values of omega, right? And you would get the Bode plot. Okay. Now, that's a lot to do. And that's why we tend to say we try to do it more intuitively with the asymptotic plots, where I have S equals S plus omega naught. Oh, at J omega equals 0, this is going to be omega naught over omega naught. The log of 1 times 20 is 0 dB, right? Then this is going to go out at some point. Minus 20 dB per decade. And where's the break frequency? Omega naught. All right. Now, if you go back and look at my notes, all that calculation and how to do a Bode plot from scratch is there. But you really need to be able to do this. And this. All right. These two you need to know from scratch in your head for the rest of your life. Okay. Now, for the second order, okay, that's the low pass, right? And what's great is that the denominator never changes. The poles would always be the same. High pass, right? And what we're going to do is take a Bode plot and find, there's some gain terms here as well that I'm just going to throw in. I'll call this gain DC. Gain midband. Gain AC for high frequency. All right. So we take a Bode plot. We got to find omega naught, the damping coefficient, and the gain. And now you kind of know the system, right? Now there's one more. And it's the high pass plus the low pass, which, right, if we were to convert this into DF2, right, we'd have 1 plus omega naught squared divided by S squared, 1 plus 2 times the damping coefficient omega naught divided by S plus omega naught divided by S squared, which would equal what? B naught plus B2 divided by S squared, 1 plus A1 divided by S plus A2 divided by S squared. Second order means 2 integrators. A summer. All right. A2 is negative. A1 is negative. We want to keep it negative. So we keep it on the positive side. The input is positive, so we keep it on the positive side. A2 is positive. We need to invert it, so we bring it on the negative side. And then before, we just took the outputs here, here, or here, but with the notch, we need to sum. This is B naught. B naught is positive, so we want to keep it positive. A1, there is no B1, right? It's here, and this is positive. Oh, well, that's easy. Keep it positive. Okay. On the exams, on the midterms, right, I was just doing low, higher band, right? And you just pulled it off. You really just pull it off of one of those nodes. The notch, you have to sum, right? And see how we're summing two transfer functions? Well, that's the parallel. So even though this is the feedback configuration, we're using the summing configuration with the feedback configuration to make the notch filter, right? So if you remember those homeworks way back when, where you said, oh, you know, H1 of S, H2 of S, right? And sum it. That was the parallel. Well, that's what it's doing. But since the denominator is the same, you know, it's easy, right? But where does H1 and H2 come from? Well, a feedback type configuration. All right. So that's a little bit more review. I'm just going to check for raised hands and spy on who's here. Okay. So we kind of reviewed a lot. And we're about to get into the new part, which is where we're going to identify a system. And no, I haven't really talked about the damping coefficient yet. And I will. We'll do that right away. Okay? Or we'll do that shortly. But are there any questions so far? Okay. So yeah, you know, what are generally are our choices? Low, high, band, notch. These are, let's say, the famous ones, right? But you can have transfer functions that don't have a name, all right? But yeah, you've kind of got to look at it and say, oh, that's a low, that's a high, that's a band, and that's a notch or not. Because, yeah, let's maybe just take an easier example. Where I'm not even looking at the phase, but phase can really help. All right, so this looks like a low pass filter, and the phase, it's gonna go down and then go down, and it's gonna go from 0 to minus 180. So low pass, right? Take the phase difference, right? Divide by 90 degrees. That gives you the order, right? So if I go from 0 to minus 180, divide by 90, that's second order. If I go to 0 to 90, divide by 90, right, that's 1. Okay? Now, the trick is sometimes you might see it something where it like tails up, or maybe it's doing something and you just haven't taken the frequency out far enough, right? You know something's going on there. You'd like to extend the plot in frequency, but you might not be able to. But what you can say is that you know there's some other order in there. All right. Now, this one we can kind of just do pretty easily because, you know, j omega very close to 0, right? Or I'm going to draw it over here. H j omega very close to 0 should give me the gain DC. So let's say this is 10 dB. Okay. So the thing is we have to convert that from dB. So the gain DC, right, is 10 raised to the 10 divided by 20, right? That gives us the okay. So that part is done. Now, in this case, it might be easier you can just read off omega 1 and omega 2 right from here and get a different kind of, you can get a different form of the transfer function, right? Where it's just S plus omega 1, S plus omega 2, right? You just like those plots where you had two real poles separated by a lot, you could just draw it out like that, right? Well, so really that's just S squared, omega 1, omega 2, omega 1 plus omega 2. All right. And then you can see that that's omega naught squared. That's 2 delta omega naught. That's just 1. Oop. Okay. So omega naught squared equals omega 1, omega 2. Omega naught equals the square root of omega 1, omega 2. All righty. 2 damping coefficient, omega naught. 2 damping coefficient, omega naught equals omega 1 plus omega 2. All right. Okay, so then the damping coefficient is omega 1 plus omega 2. What was omega naught? It was the square root of omega 1 times omega 2 and divide by 2. Well, that gives us omega naught squared, which gives us omega naught, which gives us the damping coefficient. So that's pretty much, if you will, solved, right? We found all the things for that. Now, why are we introducing this damping coefficient? Well, the thing is we've kind of been doing it with over, under, and critically damped response. We just haven't been putting it in that form, all right? So if you see a Bode plot like this, right, omega 1, omega 2, you can see 2 real roots. It's over damped, right? If you see this, where the slope is minus 40 dB at some omega, I'm going to call it, right, 1 repeated real, right, critical. And this is like, this is the critical part, or the new part. If you see this, a peak here, right, you have a pair of complex roots. And I think the intuitive way to think about it is here. Okay. Is that we have overdamped. That means we have 2 real poles. All right. Then we go to critically damped. So these things move towards each other, right, where there's 2. Then as we decrease the damping factor, or it gets more underdamped, it goes complex. So it goes this way and then up, and this way and then down. Now it could go the other way, either way, right? But this when I plot the magnitude as I'm putting in j omega, right, if I have my roots out here at 0, it's going to be high here at 0, right? The Bode plot is this way, that dimension. But notice when I have a complex root, I could have, this is going to infinity, right, out of the screen towards you, right? So that means you're going to get some kind of peak here. So if this is going to infinity, sure, it's not infinity here, but it's pretty high. And this is where this peak comes from. So the method I described, yeah, you know, if you only see one break, right, look at the phase first, right? Oh, phase, I see a minus 180 degrees phase. All right, it's got to be second order. I see 100 minus, and this is just a low pass, minus 180 degrees phase. Oh, that's just a low pass. Same here. Low pass, second order. Low pass, second order. Low pass, second order. But what's omega naught? What's the damping coefficient? And what's the gain DC? Right? Now, just a little more on that is that right, that would be second order underdamped, overdamped, a large, right, and there's 2 breakpoints, right, that would have a large damping ratio, right? Then if I had kind of 1 breakpoint, right, it would kind of do this, right? And then if I had a complex one, it would come here. And this would be small, right? Zeta equals 1. Okay. Now something to notice. We're backfitting this equation. Right? I showed you when this damping coefficient was bigger than 1. And to see it like that, it's got to be a lot bigger than 1, just so you know. All right? But omega naught is not this one, nor is it this one, and it's not necessarily where the peak is. Okay? And I guess what I'm trying to say is, what if you saw this flat response, right? You know, we have an omega. We see a plus 40, right? And you might say, oh, that's got to be critically damped. Not necessarily, okay? Critically damped would be at minus 6 dB, but you can have an inflection point at minus 3 dB. All right, and I don't want you. I think it's just best to do it with an example, right? And it's just, this is the resonant frequency of the circuit or the system, but it might not be a break point. All right. So if you see this kind of a plot, okay, it's low pass. You notice that the slope is 40 dB per decade. You notice that the phase goes from 0 to minus 180. So all signs point to low pass second order. Okay. But what sometimes people think is that, oh, I only see one break, therefore it's got to be critically damped, so there's only one real root. Well, no, this point would be at minus 60 B if it was critically damped. So in fact, there's a more generic way to do it, is that find gain at H equals J omega naught. Ah, okay. So what that would, so we have omega naught squared, right? We have J omega naught squared, right? Because we're substituting S equals J omega naught, right? We have 2 zeta omega naught times J omega naught plus omega naught squared. Well, what's that equal to? Well, here's the thing. We found the gain DC for S equal to J omega naught. J omega. 0J. Okay. We already found that. So J omega naught squared is minus omega naught squared. Omega naught squared is omega naught squared. They cancel. Then we have 2 damping coefficient omega naught times omega naught, but the J is still there. All right. What does that imply? Well, notice the omega naughts still cancel out, and we're left with H S equals J omega naught, the gain DC divided by 2 damping coefficient J. Well, the magnitude right just equals gain DC. Okay. Where did this number 3dB come from? Well, I'm going to tell you is that I find the minus 90 pot spot, come up, and I just told you that it was minus 3 dB. All right. How did I know it was minus 90? Well, we can look at the phase. Well, you have gain DC, because this is the spot, this is what we're looking at, right? At a phase angle of 0 degrees. Then we have 2 times the damping coefficient. And what's J? Plus 90 degrees, right? So what is the phase at this point? Minus 90 degrees. So this case, you just find the crossing point that, oh, minus 90. Wherever that is, that's omega naught. Run up, and then you find the gain at that point. Well, it works back up here too, right? Now, now this is a little bit harder, right? But somewhere in here, the gain, it's not perfectly flat slope, okay? It's changing, and you find it where it's 90, right? That becomes omega naught. That becomes the gain at omega naught, and you'll find that when you calculate it, the damping coefficient will be bigger than 1. So to go back, so it's doing it with the phase is generic. All right. So in this case, the gain DC, right, was equal to 1 because it was 0 dB, right? The gain at j omega naught equaled 10 to the minus 3 divided by 20. Right? So gain DC, sorry. Oh, wait, you know what? Something was wrong. You're right, because it should be 0.07. Hold on. Yeah, it's... I don't know what I was thinking. Oh, man. What am I doing? Yeah. God. So the minus 3 dB point is actually the half point, right? Equals 0.5, right? So 0.5, the gain at DC is 1 divided by 2, right? It's the square root of 2. So that means zeta is 0.706, regardless of wherever that omega naught is, right? The important thing was find the omega naught at the minus 90, right? Now you know where, now you know what omega naught is, then you know what the gain is at omega naught, then you can find the damping coefficient. All right. You already have this. Okay. And that could be 10, 20, whatever. But what tricks people up is they say, oh, it's second order. This must be minus 6 dB. And then they go and they don't really know this is a very important coefficient. It's the Butterworth coefficients. Okay. And Butterworth filters, you kind of take a semicircle, right? And yeah, if you have two poles, you split them up so that the difference in phase between them is equal. If you have 4, right, you would put the poles here. If you had 5, right, you would, these are all complex pairs of poles. So if I had 5, I'd have a 5th order circuit. Right, if I had 4, it'd be a 4 order. three order, two order. But you take those complex, this is in filter design, that's where you choose them to be. And what you do is you get a really flat response, but you keep getting a sharper and sharper roll off, right? Almost like that as the order goes up. Now, as the order goes up, the phase delay goes longer and all that. But that's for later. Now, we look at it, it's got to be a high pass. Let's do some phase. Oh, I'm gonna. So it's high pass. The phase goes from 180 down to 0. Okay. And now, yeah, we are going towards a different, we're backfitting a different equation. We have S squared gain AC, oops, right? S squared plus 2. Well, how do you get it? You know, let S go to infinity, find gain AC. So gain AC equals 10, just like that. Now we can, I can substitute J omega, and we're going to find, let's just do it as a complex number review. All right. So what do we have on top? We have J omega squared, which equals what? Minus omega naught squared. Over here, we have J omega naught squared, forgot the S, to omega naught squared J plus omega naught. Well, these two cancel each other, so I get minus omega naught squared divided by wait, oh, and sorry. The omega naughts cancel out, right? So I get GAC phase angle minus 180 because of the minus sign, right? But it's all real. To with 90, gives us which gives us 90. All right. So and this is for a second order system. A first order system would be 45, and so on and so on. Now, the bandpass gets a little more complicated, and I do have notes that once you get this, the other one should come pretty straightforward. So here's my omega naught. All right. So, excuse me. So H j omega naught equals 10 to the 40 divided by 20, which is 100, but that's also supposed to equal the magnitude of the gain at AC divided by 2 delta. Is that a question? Okay, sorry. So the damping coefficient equals, I think that was 0.05. So yeah, that's really underdamped. Okay. Well, look at the peak. I mean, the AC gain is 20, and this goes up to 40. So yeah, that's really underdamped. Now, yeah, on the homework, yeah, you'll see. You got to choose omega naught. I'm just saying that happened to be omega naught, right? Could be a, and yeah, if you're pulling it off in frequency, right, then omega equals 2 pi f, right? That's something to remember. Um, and yeah, there's some trick questions in there where normally, yeah, we have a low pass filter. This keeps going down forever. Well, I can have something that goes down and then evens out. All right. So, right, what if I had S plus 1 or Mm. Oh, something like that. So everything that I've said, it's all right here. Okay. Now you should be able to follow along. And I might have even made a video, but a lot of times I'm just reading the slides anyway. Hopefully I gave you a little bit more to go on. But yeah, we start with a simple low pass and we go at minus 45 degrees. Because I think at first doing the magnitude seems easier, but really, you look at that phase and you can find omega naught like unambiguously. Trying to find a minus 3 dB point when the poles are really close, well, it might be really minus 6. Doesn't matter. If you just find the total phase difference or kind of like the phase change, right? So now, yeah, I start off with a second order high pass that's overdamped. You can really see the two breakpoints. Now, yeah, on the homework, you're going to be doing it by eye. Just be careful. But yeah, it's graded as if you don't have LT spice and you're just pulling off the things. So here, the bandpass, yeah, it is. The thing is how do you find this mid-band gain? It's just not as it's not as straightforward as, oh, set it to 0, set the frequency to 0, set it to infinity. Well, you're at the mid band. And notice the phase goes from plus 90 down to minus 90, right? But that's still a 180 degrees phase shift. Well, you split the difference and omega naught will now be at 0 phase. So it's usually in these second order systems, you just find the phase difference, low pass 0 to 180, high pass 180 down to 0, band pass 90 to 190, and just find the midpoint. Artem, you had a question? Well, you'd think so, but yeah, I mean, in this case, it does look symmetric. Yeah, but how do you find to find the gain midband? There's actually two ways. One where you're a lot less, where you're down here. One where you're a lot more, down there. Then when you solve for that, right, I just extract it either at minus 90 or 90, and you can come up with it, right? Then once you have that, so to find the midband gain, you still come out here, you come out here, you get the same answer, all right? But see how it's like minus 90, well into minus 90? You can just pull it off from there. Here's plus 90. You can pull off the gain gain from there. So it's both, they're both at minus 40. But one, the frequency is this with a gain of minus 40 dB. The other one, the frequency is 100 megahertz, right, with a gain at 10 to the minus 40. Omega naught, you pulled right from there. So now you have it. You just say you can go here or you can go here. Fine. Then once you have that, yeah, instead of finding the damping coefficient at plus 90 or minus 90, you find it at 0. Okay. Now, yeah, as you get more and more underdamped, it narrows. Okay. And then here's, you know, the damping coefficient from 0.1 to 10. So there you can see a peak, then it flattens, and then you see like 2 breakpoints. But notice, it passes minus 90 degrees phase all in the same point. That's what's so great. So you just find minus 90, and then now you got omega naught, then you can find this, then you can do that. Same with the high pass, except now it's 90. Same with the low band pass, except, yeah, 0. Thank you, Devin. I guess it's about time for 112, so I'll just say goodbye.